Okay, so ladies, we are going to talk about some really basic examples of concentrations. Do some really basic calculations, and also talk about like different ways you can define concentrations of substance. But let's start. What do you think is meant by concentration? Right. So it's the amount of a solute and a solvent, for instance, right? And there's just like, you know how there's like different ways you can measure mass? Different ways you can measure concentration. So I'm going to show you some examples that you might come across in your everyday life. Definitely examples that you're going to come across in your chemistry textbook, okay? The one we'll end up with is the one that you're most likely going to need to understand, which is moles per liter. We've been talking about the mole a lot. But we're going to talk. We're going to start off with a different concentration, which is percent mass over volume. And this is a really easy one to understand. Basically, it's just the mass of a solute over the volume of the solvent, and the volume of the solvent is generally 100 milliliters. Okay? So, in this case, we have an example, a saline solution, which is basically a salt solution, and it's 0.9%. So 0.9% actually represents 0.9 grams for every 100 milliliters. Okay? So a 3% solution then would be the same as 3 grams for every 100 milliliters.
So it's not like the amount of the solvent in the solution.
It's the amount of the solute in the solvent.
Yeah.
Right. But it's the amount in terms of mass over the volume of the solvent. The volume of the solvent is given as 100 milliliters. A saline solution of 0.9%, that's the concentration of solute in your blood. So if you've ever been to a hospital and someone is getting IV and you see it says saline solution, it's 0.9%. What you want to do is you want to give someone the same concentration of solutes that is going in the blood that the blood already has. And we'll talk about later on what happens if it's not the same. Something will actually happen to your blood cells, the red blood cells, white blood cells, all that stuff. So you might come across this in the hospital. 3%, that's about the concentration of salt in the ocean. Dead Sea would be much higher. The calculation is really easy. But let's say I asked you to make the solution. I said, okay, I want you to make 30 milliliters of it. Yeah, how would you make a 30 milliliter solution that is 0.9% sodium chloride? So we're going to say the saline is sodium chloride. So it's NaCl. So the concentration is 0.9 grams for every 100 milliliters, right? And we want to make 30 milliliters. So what you're going to see in this little presentation is all about ratios. It's all about setting up ratios because the ratios have to be proportionate. So a 0.9% solution is 0.9 grams for every 100 milliliters. The concentration is the same. So the 30 ml solution is still, that 30 ml solution is still a 0.9% solution. So the ratio of salt to water has to be the same. So all you do is you solve for x. So x would be 0.9 times 30 over 100. You'll see the mils cancel out, and you're left with 0.27 grams. So the ratio of 0.27 to 30 is the same as 0.9 to 100. Okay? Pretty easy stuff. So that's one example of how to measure concentration. I'll show you a couple others that are basically the same thing, but you might not see 100 milliliters. They'll have it in deciliters. So, for example, Hemoglobin. Sorry. Hemoglobin. That's important. Go to the doctor, like your blood work. One of the things they'll check for maybe is your hemoglobin count. Why is it important?
Isn't it like prevent clotting?
No, it
Or
doesn't.
makes it red?
Well, why does it make it red?
Because of red blood cells? I don't know. Oxygen?
It's the color of the hemoglobin bound to oxygen. Forms a red color. Now, it's not important that it's red. Why it's important is that it carries oxygen. So if you don't have enough hemoglobin, then that means you're not carrying enough oxygen, you'll be tired. So you go to the doctor, they'll measure your hemoglobin, and they'll give you back, they'll probably just tell you it's too low. But if you want to know what your actual number is, there's a concentration to it. So what's normal for females is a range between 12.1 to 15.1 grams per deciliter. Now, a deciliter is the same as 0.1 liters, which is the same as 100 milliliters. So if you really think about the previous example, what was it? It was mass over 100 milliliters, right? So it's exactly the same thing. So for a female, the range is 12.1 grams for 100 milliliters, all the way up to 15.1 grams over 100 milliliters, okay? So let's take the upper limit. Let's say we're looking at, what's the upper limit? 15.1 grams. So 15.1 grams or 100 milliliters. If we were to measure 1 liter of blood, how many grams of hemoglobin would there be? Well, what's 1 liter of blood? Same as 1,000 milliliters, right? So this would be the same as 1,000 milliliters, correct? So the ratio of 15.1 over 100 should be the same as x over 1,000. I can go ahead and solve it. X would be 15.1 times 1,000 over 100. And that will give me 151 grams. Because again, it's proportional, right? So the upper limit would be 151 grams per hemoglobin. We can see that there's a problem if there's not enough hemoglobin. If there's too much hemoglobin, it actually could interfere with blood flow, which is that means your blood's too thick. That could be a problem too. All right. So, yes. Okay. So but again, it's the same. It's still mass over basically 100 milliliters of a solvent, right? Okay. Next example. Or next two examples. Sugar levels. You go to the doctor. Maybe they want to do sugar level tests on you to see if maybe you are normal or maybe if you're pre-diabetic. If you're pre-diabetic, your levels will be higher than normal. So what's normal? Normal is between 100 to 125. But look at the unit, okay? Milligrams per deciliter. So what do you see? You see mass over 100 milliliters, right? Same thing. Mg is milligrams, right? So 100 milligrams would be the same as 0.1 grams. So the range could be 0.1 to 0.125 grams per 100 milliliters. That's what's normal. Fasting means that you don't eat for a certain amount of time, right? Maybe a doctor says, okay, don't eat past 10 o'clock, or definitely don't eat in the morning, because if you eat in the morning, then your sugar levels will go up, and they won't know if it's up because you ate, or if it's up because you got a problem. Okay? So you can see that for glucose levels, it's the concentration unit is mass over 100 milliliters of solvent. for blood alcohol levels, the famous take the breathalyzer test, what your alcohol, it's actually the same thing. The unit that they give you, they say, they give you the number, so you probably all know the number. It can't be higher than 0.08. But what is that actually? What is that number? It's actually the same thing. It's mass over 100 milliliters of water. Okay? Now the 0.08 is 0.08 grams. So 0.08 grams over 100 milliliters. Okay? Because 0.08 grams is actually the same as 80 milligrams. Right? Same thing. But I believe now if your levels are 0.05, even if they're under 0.08 but they're 0.05 or higher, you will get suspended, right? Yeah. Okay. So that's an example of, so all of those examples are mass over 100 milliliters of solvent. Another example of concentration could be mass over mass. Now, except for one of them, which is the one for water, but so you can see here in these examples, it's mass over mass, mass over mass, mass over mass, mass over mass. This one's milliliters over mass, but that can be converted to mass, mass over mass. This one here is for LD50. So if you look up LD50, it'll give you the concentration. So for glucose, you saw the concentration was mass over 100 milliliters. But for LD50, it's often expressed as mass over mass. And the LD50 is actually an interesting one because I was looking at, okay, what kind of interesting concentrations can I give you as examples? This one's not in your book. This one is the one that if you had a population of individuals and you gave, let's say we were looking at mercury, all right? And we gave about 100, so let's say for every 1 kilogram that a person weighed, for every 1 kilogram a person is. So like, for example, if you're 100 kilograms, then you would need more. But the ratio is still the same. So for every kilogram of a person, if you had in you about 100 milligrams of mercury, there would be 50% chance that it would kill you. So you would expect that if you had a population of individuals, say 1,000 people, and their mercury levels were about 100 milligrams for every kilogram, then half of them would die. Or if you were to look at the botulinum toxin, it's a very potent toxin from a bacterium, and the levels were 5 nanograms for every kilogram. In your population, you were testing a population, and that was a concentration of the toxin that, again, half of them would die. The LD50 is a prediction that at this concentration for this toxin, half your population will die. That's where the 50 comes in.
How do you know that? Yeah.
Testing.
So they don't pay you, you wouldn't be able to give it.
So they wouldn't do this on humans. They would do this on things like rats. So they would take rats, a bunch of rats, they would give them a certain amount of a toxin. And then, by the way, the word toxin, you look up on the board here, toxins include things like glucose and salt and water, things that you normally ingest, because it's all about the concentration. If you have too much of something, even though it's safe, it could kill you. Even water could kill you. So, yeah, this is testing on animals. So how do you know that 50% of your animals will die? If you give them this much of a toxin, you have to actually test it out.
Is it like that much for, like, say you have like a population of 100 people,
Yeah.
and you put that much of it, like each person consume, or like?
So if you had 100 people,
Yeah.
and you were to measure the amount of alcohol they had per kilogram, and the concentration was 7,060 milligrams per kilogram, then you would expect half of them would die.
You find it the concentration and not the
No. It just says that if people have that concentration of a toxin in their body, then at the LD50 is the concentration that you have to have of that toxin in your body that gives you a 50% chance of dying.
So would you be able to give us that question on test?
We'll do it right now. So, how much would a 50 kilogram person need to consume for there to be a 50% chance of death? So, let's pick a toxin. Let's say water. Okay, let's say water. Let's say water is a toxin. So, the LD50 for water is 90 milliliters per kilogram. So we'll leave it as milliliters. So the LD50 is 90 milliliters per 1 kilogram. How much would you need to consume in one sitting, not over the course of a day, at one time? So again, the proportion, set it up. So 90 mils per 1 kilogram is equal to X over 50. Solve for X. X would be 90 milliliters times 50 kilograms over 1 kilogram. X is equal to 4,500 milliliters, which is the same as 4.5 liters. So, if you can't do this experiment because it's unethical, and this was done on rats. So if you assume that it'd be the same effect on rats, the idea would be this. If I took a population of 1,000 individuals and I made them drink 4,500 liters of water, and each individual was, imagine magically speaking, each individual was exactly the same size, 50 kilograms. Or if I gave them enough water so that the concentration of water relative to their mass is 90 milliliters per kilogram, then half my population would die. That's the LD50 component. Yep.
Is there something like LD100?
Yeah, you can just keep testing, I guess, until everyone dies. At this concentration, everyone dies.
Okay. So
Yeah.
if I consume, so that doesn't necessarily mean it has to be double, right?
No. Who knows what it would be? Unless you test it out, you won't know.
So if I consume like that concentration of water, 4.5, like 90 mils per 1 kilogram per mile.
If you consume enough water so that the concentration of water relative to your
my weight is 90 mils per 1 kilogram.
Right. Yeah. So you got to work out how much water would you, now whatever, your body is mostly water. I'm talking about how much more water would you have to add to your body. Now this actually happened. I don't know if you heard the story about a marathon runner that ran a race. What happens when you run a race is you sweat, you lose salt, you lose water. You have to replace the salt and water, going back to the saline solution. What happens if you drink all the water and no salt, it changes the concentration of the solutes in your blood. And if it thins out your blood too much, dilutes it too much, then that could be fatal. And that is what happened. Now the condition is hyponatremia. Very important for you guys in science to understand prefixes. Hypo means below. Hyper means above. So hypo means below. Hyponatremia means that your salt levels are low. So hypernatremia would mean your salt levels would be too high. So there's an example of concentration, but you can see that it's usually mass over mass. And the example we did was volume over mass. So this is a different example of concentration. So let's do the next one. So let's look at Another one that you might come across. This one's a pretty common one when we talk about things like climate change. And you want to know the amount of gas in the air. So you might have seen this on some chart regarding greenhouse gases. They often give you the concentration in like parts per something, right? Or maybe we're measuring the amount of a toxin in the lake. It's usually parts per something. So it's either parts per million, ppm, parts per billion, ppb, or parts per trillion, which is ppt. I didn't put up there. It's usually a mass-to-mass relationship. So what that means is that if I have, like for example, 400 parts per million, that means that for every 400 grams of carbon dioxide, it would be in 1 million grams of air. So that would be CO2, and that would be air. Okay. So if it's, for example, the one below it, ammonia levels, so at 0.73 parts per million, that means that if I have 0.73 grams of ammonia in 1 million grams of water, it would be considered dangerous because it's parts per million. If it was parts per billion, then it would be over 1 billion grams. If it was parts per trillion, it would be over trillion grams. Just 10 to the 12. So let's look at how much ammonia would be, given the dangerous limit, how much ammonia would there be, what's the mass of it, given at that level, for half a liter of water. So the level is, as you saw, 0.73 grams for 1 million. And if you want to write it as exponents, what is the mass for half a liter? Now, half a liter, though, is how many grams? What's half a liter? How many milliliters? So it's about 500 grams, right? 5 times 10 to the 2. So how many grams of ammonia are in half a liter of water at that dangerous level of 0.73 parts per million? You getting tired of this? Solve for x. So 0.73 times 5 times 10 to the 2 over 1 times 10 to the 6. This is grams. This is grams, grams, grams. That'll cancel out. So what's x? Zero point what? Should be 0.00036 something. Is it about 0.00036? Yeah, which is the same as 3.6 times 10 to the negative 4. Okay. How's the math so far? Easy, right? Okay. Oh, you notice it's all the same, right? Okay, let's pause it then. Hold on. Okay. Alright, let's look at some other examples. And actually, really, the last ones are all going to revolve around the mole. Okay? And this is probably the most important one for you because we've been talking about the mole, and most of the examples in your book are going to revolve around this concentration. The concentration is moles per liter, and it's often written as big M, but big M is confusing because we use that as molar mass, right? So that's okay. Not a big. We can handle that. It's not a big deal, all right? So the concentration here is moles, number of moles per liter. And we've been working with the mole for a while now. So let me give you a practical example. You go to a doctor and they measure cholesterol levels, right? And they'll tell you if it's too high or too low. It comes back as a concentration. So the concentration is generally if it's less than 5 millimoles per liter, you're okay. Now, what's a millimole? Okay. So so moles, MOL. So moles per liter is MOL. That's the big M. Okay. Little m is millimoles, which is just simply is 1,000th of a mole. No, because that's what this is. Moles per liter is big M. So millimole, just like what's a milliliter? Thousands of a liter, right? What's a milligram? Thousands of a gram, right? So it's the same thing. So millimole is 1,000th of a mole. So let's say you have 40 milligrams of cholesterol in half a liter of water. What would that concentration be? Okay. So first thing, because there's a moles per liter, right? So what do you think the first thing we should do is? Find the number of moles. Alright, so first thing is you find the number of moles. Remember the formula? Mass over molar mass. Now the confusing bit is we've used big M to represent molar mass. So if you need to remind yourself, this is molar mass, give yourself a little M maybe beside it if you want. Molar mass. It's up to you. It's ingrained in your brain. So how many moles is this? Well, it's 40 milligrams over the molar mass Alright. What's the problem here before we proceed? Right. Milligrams. So 1,000 milligrams is 1 gram. Or 1 gram is I'm sorry. 1 milligram is that. 1 milligram is 0.001 grams. Alright. So how much is 40 milligrams? 0.04 grams. Okay, so what's that in terms of number of moles? 0.04 grams over 386.65 grams per mole. What is that? 1.03 times 10 to the power of -4 moles. Okay, so there is the number of moles. Now, the concentration is in moles per liter. So the big M, moles per liter, not to be confused with this big M, is number of moles over the volume. Okay, that's our formula for concentration. So let me should change the color so just to maybe I won't change the color. Oh, Ford's not responding. Let's try that again. Okay, so number of moles over the volume. So 1.03 times 10 to the minus 4 moles over 0.5 liters. The concentration then would be 2.06 moles per liter, or 2.06 big M. Okay? Big M. So there's a concentration. But our reference point is, I'm sorry, that's 2.06 times 10 negative 4. We got the negative 4 there. Times 10 to the negative 4, big M. So this is times 10 to the negative 4. Okay. Is that normal? Is that okay? Is it safe? Would the doctor be concerned? So we got to convert that to millimoles. So if 1,000 millimoles is 1 mole, or 1 millimole is 0.001 mole, then how would we convert this? What is it? Times it by 1,000. Very good. So remember, this okay, so that was our concentration, right? 2.06 times 10 to the negative 4 moles per liter. Okay, so now we're going to convert moles to millimoles, because the reference point is in millimoles, and we need to speak the same language to know if it's okay. So we're going to convert moles to millimoles. So we have moles, so 1 mole is equal to 1,000 millimoles. So we got to multiply it by 1,000. Millimoles per mole. That will get rid of the mole, and you're left with 2.6 times 10 to the negative 1, or 0.26 2.06 millimole per liter. 0.206 is less than 5, so we're okay. This person would be fine.
I put my head down and
Yeah, I'm going to explain that next. Yeah. So, girls, and remember I'm recording this, eh? So can you relax? It's fine. Are we okay with the concentration of 2.06 moles per liter? Sorry, 2.06 times 10 negative 4 moles per liter? To millimoles, yeah. That's all. We just convert it to millimoles, right? Yeah. 0.206. 0.206. Okay. We're almost done. Going back to the saline solution. So you go to the hospital and you get hooked up to IV. They give you a 0.9% saline solution. Well, what is that? Okay, let's first figure out what is that in moles per liter or millimoles per liter. Okay, so we're going to do like a very similar example. So 0.9% was what again? Yeah, it was 0.9 grams, or it was 9 grams for every 1 liter. Because it's 0.9 grams per 100 milliliters, which is the same as 9 grams for 1 liter. Now, how many moles is that? I'll explain that in a second. So, how many moles is that? We want this in moles per liter. So how many moles is that? Okay, well, sodium chloride, NaCl, has a molar mass of about what? 23. Sodium's 23 and chlorine is 35.45. So that's about 58.5. We'll round it off. Correct? So let's figure out how many moles is this. So number of moles is mass over molar mass. So that's going to be 9 grams over 58.5 grams per mole. So how many moles is that? I'm going to explain that in a second. So how many moles is 9 grams? 0.15? what? That's it? So 0.15? So we'll round it up to 1.154. So 1.54 moles. So far, all we did was we converted the mass to moles. We've done that 1,000,000 times now, right? So, this solution of 9 grams per liter can be converted to moles per liter by just converting the mass into moles, right? So we know that it's 0.154 moles. So 9 grams per liter would be the same as 0.154 moles per liter. So that means the concentration is 0.154 big M or moles per liter, however you want to write it. Okay? Or big M. I'll just put big M in brackets. So far, so good? Now, if you want to convert that to millimoles, times it by 1,000. Because as we saw, 1 mole is 1,000 millimoles, right? So if we multiply this by 1,000 millimoles per mole, the moles will cancel out, and you'll get an answer of 154 millimoles, correct? Millimoles per liter. So now that is the similar, it's the same procedure we used in the previous question. Okay. Now milliosmoles, so you'll notice that, yeah, so, so you see this, right? So this refers to, and we're going to look at this. We're actually going to investigate this one. This refers to what happens to a solute when it goes into water. So what happens when a solute goes into water is, we talked about the crystal splits up. Now, let me just scroll down a little bit, give myself a little bit of room here. So if it was, like, for example, and you saw what sodium chloride looks like, right? What is it? It's a cube. It's a very nice cube. Beautiful cube. But what's in that cube? If you were to zoom in to the level of the molecule, what would you see? You would see this. You would see NaCl. And you would see a lot of them. So each of these little dots would be a molecule of NaCl. But what happens when you dissolve something? It breaks up. But what also happens to an ionic compound is the compound itself splits. So in water, not only do the molecules of sodium chloride split, so these molecules will split and be free, but the sodium and the chlorine will split into their ions. Now, let's do the math. One sodium chloride splits into 2 ions. So, what was our concentration for moles per liter for 9 grams of salt in 1 liter? What was our concentration? Yeah, millimoles per liter. Sorry, millimoles per liter. Okay, but if each sodium chloride splits into 2 ions, then the concentration is actually 308 milliosmoles per liter. In other words, no. Remember the definition of a mole is what? Number of particles. So if I have 1 mole of sodium chloride, and that splits into 2 ions, then I have 2 moles of the ions. Right? So for milliosmoles, you figure out how many moles you have per liter, and then you figure out what the ion does. If the molecule splits into 2 ions, you multiply by 2. If it splits into 3 ions, you multiply by 3. If it splits into 4 ions, you multiply by 4. Now, if it doesn't split at all, then you leave it. So like, for example, sugar is not an ionic compound. It doesn't split. The sugar molecules break up, but the molecule itself doesn't break up. So it doesn't form ions, therefore you don't multiply by anything. You leave it the way it is. We'll investigate this in detail. We'll do an experiment with this one. Okay, I'm thinking maybe we'll do it tomorrow. And so again, we're going to talk more about moles per liter. The last thing I'm just going to mention, I'm not going to really do much more with this, is here are just some other units. So how many of you, when you pick up a can of something, you look at the sodium levels? Yeah. So the sodium levels, what's normal is a range of about 135 to 145, what are called milliequivalents. A milliequivalent is the same as a millimole. Okay? So the same as a millimole. So for example, for an ion that's monovalent, which means it's +1 or -1. If it was +2, then it would be called divalent. But for an ion that's +1 or -1, the unit, and I'll be honest with you, you're probably never going to come across this. I just thought I would put it up there. Maybe. If your levels of sodium are below this, again, that condition is called hyponatremia. It's an ion that has one, like it's +1, basically. So a divalent would be like calcium, which is +2. Yeah. Yeah, but this is not as important as the other stuff. The other unit that you may come across in your life is as you get older, things start falling apart. Sometimes they prescribe things and are called international units. I don't know if you ever come across that. Yeah, like vitamin D is prescribed in internet. Like vitamin C is usually given in milligrams, but vitamin D is given in this arbitrary unit called international units. We're not going to talk about it. I just want you to be aware of it. Okay? So like insulin levels. So if you go to the doctor and they give you insulin levels, the unit is in these international units. So it's actually a micro international unit for every milliliter of blood. So it's not in milligrams per milliliter. It's not in moles per liter. It's not in millimoles per liter. It's not in grams per grams. It's in this thing called international units.
Who made it up?
I don't know. Anyway, so those are some examples of different concentrations, but we are going to focus on the ones with moles per liter. That's the one that we're going to focus on. So I'm going to stop there, ladies.
Whoa, I need to look